Hello, friends. Today we are taking fourth lecture of nanoparticles, metallic nanoparticles. So that in that now let us consider semiconductor, semiconductor nanoparticles, nanoparticles. So we understood the metal nanoparticles already. In metal nanoparticles, we observe the surface Plasmon resonance, and semiconductors are quite different from conductor. Conductor conducts or give the conductivity, electric conductivity at 0 Kelvin, but semiconductors are not. That is a major difference. The conductivity is always less than conductor. Okay, so that conductivity is less than conductors. Conductivity of semiconductors is less than conductors. Okay, and so semiconductors having conductivity equal to 0 at 0 Kelvin, so that sigma represents the symbol for the conductivity, and so sigma gives finite value. Sigma is increases with the temperature. At T is greater than 0 Kelvin, semiconductors conduct. The semiconductors are characterized by, these are all semiconductor are characterized by band gap. So that the band gap we get in semiconductors, but band gap is 0 in case of conductor. So that what is this band gap? Let us see. So that this is the band gap. So in any material, so consider an atom. Okay, so this is the nucleus, this having different energy levels. Okay, so this is the isolated atom. So when you take bulk material, okay, so in case of what happens, n number of atoms. When n number of atoms group together, what happens? When n number of atoms group together, so consider here the energy levels. Here this is, we get the not only one energy level, but each energy level split into the number of energy levels. Similarly, this one is split into n number of energy levels, and similarly this is split into further n number of energy levels. Okay, so that what happens here, you see the difference here is large and difference energy level is less. So for that purpose, as you go higher and higher energy levels, so that this is when you take this higher, another one higher energy level, this is so split into different energy level, and these two are superposed. So what happens? Consider in this case 1, 2, 3, 4, 1, 2, 3, 4 electron in atom electron field up to this, and this is empty. Then what happens? Of course, another one energy level comes. Then what happens? In this case, this electron comes to this place, and this above all the any energy levels which are coming, all are superposed up to infinity. So that what happens? These electron become free to move anywhere, and these electrons are called free electrons. And so that from this energy level a band will form, from this energy level another band will form. So that the band, the topmost band which contains electron is valence band. The above the valence band, that is conduction band. Okay. So that what is valence band? Valence band is the topmost. This become band now. This energy level become energy band. The topmost energy band which contains electron, that is called valence band, and above the valence band which is empty, okay, here that is conduction band. So that usually what happens, the valence band is actually the topmost band which is completely filled, that is called valence band. For example, you know that s orbital, how much electron it fills? It fills 2 electrons. If the energy band corresponding to s is completely filled, that having 2 electron, that is called completely filled. Okay. If it is topmost, for example, in case of the sodium, here what happens? Here in case of sodium, 1s2 sodium, 2s2, 2p6, 3s1, because it having atomic number 11 electrons. Okay. So that what happens in this case? So p orbital is completely filled, and s orbital is, which one is topmost orbital which is completely filled? P. 2p, which is the energy level above valence band, above completely filled band, that is 3s1. Here this, the band corresponding to this is called valence band, and this is called conduction band. Conduction band is either partially filled or completely empty. In some respect, it is completely empty. Valence band is completely filled. So that in case of the metal like sodium, okay, so valence band is completely filled, conduction band is partially filled. This partially filled electron which is present here, valence band and the conduction band is overlapped here. Then means what? Next 3s1, 3p, here 0 electrons are there. So that this is overlapped with this. Is it right? And 3p, 4s, whatever, 3d, no electrons, again 3d, 0. So that electrons are free to move anywhere. And these are called free electrons. We get free electrons in case of metal. But such free electrons are not available in case of semiconductor. In semiconductor or insulator, valence band is completely filled and conduction band is completely empty. But here I said valence band is complete and conduction band is overlap in case of metals. Conduction band. But in semiconductor, it is not possible. There is the gap between the valence band and conduction band. How it happens? So that consider this is conduction band. This is conduction band. Okay, we get the number of energy level, and this is valence band. Okay, so that we get there is a gap. This is forbidden gap between valence. That this forbidden gap is not appearing in metal. So that this is lowermost energy level in conduction band. This is conduction band. This is valence band. Okay, this is, we call this as EC, conduction band minimum. What is this? EV, valence band maximum. And this difference, what we call energy gap. So that EZ equal to EC minus EV divided by 2. This is the energy gap. Okay, so that not divided by 2. EC minus EV. EC minus EV is called energy gap. So like this, we this is characteristic of energy band gap. It is we get in case of the semiconductors. Now there are number of semiconductors. So that I think you heard the silicon. It is semiconductor. So which having energy gap 1.12 electron volt. Okay. Germanium, this is semiconductor, most prominent semiconductor these are. So this is 6-7 electron volt. Okay, electron volt. So that this is the normally which are used in the most of the electronic properties. Because the electronic property is more completely depending upon semiconductors nowadays. Okay. Now, so there are the silicon and germanium. Usually these are all, what is that? Come to fourth group. Fourth group. Why fourth group? Because the valency is 4 for them. Okay, so that they have 4 outermost. Almost all semiconductors having the fourth group, the elemental semiconductors. For example, diamond, carbon in the form of diamond. Okay, so this having 5 electron volt. So this is also the fourth group. The carbon is diamond. Diamond is semiconductor, but we don't put this into semiconductor because it's an energy gap. So energy gap is very high. Why if the energy gap is very high we don't put? Because what happens in this case when the EC and EV, so when electron completely fills valence band at 0 Kelvin and no electrons at conduction band, but when some energy is supplied to this electron goes to the conduction band. But these electrons immediately come back to the valence band. But if they did not come, they form, this is a gap here and 1 electron in the conduction band. If voltage is supplied at this direction, electron goes in this direction and holes are moving in opposite direction. So that this is one atom I have shown. There are number of such atoms are there in semiconductor. So that the electron is flowing in this direction, the holes are. so that we get the current in the semiconductor. Okay, so that the whole due to two current carriers, one is electron and the one is holes there are, but in conductor only one current carrier, those are electrons, but here both holes and electrons are current carriers. For that purpose, we know that the semiconductors are classified into different intrinsic and extrinsic semiconductor. Intrinsic semiconductors are the pure semiconductors, okay, like germanium and silicon, and the drawback of the intrinsic semiconductor is that the conductivity is negligible. Why negligible? Because one electron goes in this direction, one hole in this direction. That the effective current cancels here practically. But a little bit we get a current we get because the mobility of electron is larger than the mobility of hole, because electron in the conduction band, hole in the valence band. Okay, so but what happens, that is not sufficient for the different various applications of electronic circuits. So for that purpose, intrinsic semiconductors are having very much limited applications. But there are extrinsic semiconductors. What are extrinsic semiconductor? Extrinsic semiconductors are doped semiconductor. Doped means what? Impurity is added into the pure semiconductor. What are the impurities? Trivalent and pentavalent impurities are added. Okay, so that in case of extrinsic semiconductors, so that addition trivalent. What are these trivalent materials? So gallium, okay, so that indium, gallium, indium, boron, okay, so that etc. are these are all trivalent impurities. When trivalent impurities are added to this the pure semiconductor, we get P type semiconductor. Addition of P type semiconductor. What is this P type? P type having holes are the majority carriers and electrons are means the most of the electrical properties of the material is due to the holes. But in case of the pentavalent, addition of pentavalent, what are those pentavalent material? So the phosphorus, arsenic, etc. are the pentavalent material. Okay, this pentavalent material here, so that this gives n-type semiconductor. In case of n-type semiconductor, electrons are the majority carriers, means electron having high value, so that we get effective current. Okay, so that here the n-type semiconductors are, when pentavalent materials are added to silicon and germanium, we get the n-type semiconductor. And another one, so this way p type, intrinsic, extrinsic, p, and again extrinsic is p n type semiconductor, so that we classify, and the whole the electronic industry is depending upon this type of extrinsic semiconductor. Means what? Impurity added semiconductors to impurity added to the silicon and the germanium semiconductor, transistors, diodes, rectifiers, filters, what not, those are used in the electronic circuits, or due to these the electronic circuit nowadays, the present that is depending upon the silicon technology, microprocessors, all these. Okay, so there is another type of classification we have. One is indirect band gap. This is another one, band gap. And another one, direct band gap. What is this indirect band gap? So that indirect band gap, this is the elemental semiconductors. Okay, this is compound semiconductor. Compound elemental semiconductors, and so that this is compound semiconductors. So that what are these elements? Again, this is similarly silicon and germanium. Silicon and germanium are the for example for this. Here compound semiconductors, the compounds of so 3 and V are added together, compounded together. Okay, or 2 and 6 are compounded together. Okay, compounded together are called the these are the direct bandgap semiconductors. Okay, and another one is so IV and IV. Fourth. Finally, what from this you come to know that the total become 8. Okay, so 3 plus 5 8, 2 plus 6 8. So then and what happens? This is 4 and 4 8. That should become like this. So that there are different classification in case of the compound direct bandgap semiconductors. Now, so that there are silicon and germanium are there. Again, what are these? So what is the use of this direct bandgap semiconductors? So indirect, here in this case, the importance of direct bandgap semiconductors is that here indirect bandgap semiconductors are useful only for the electronic properties. Indirect bandgap used only for electronic properties and in some cases photovoltaics. Okay, photovoltaics means photoconductivity. In case the silicon solar cells are available, so that electronic and the photovoltaics only. In this case, indirect bandgap semiconductors are useful. But what happens in case of direct bandgap semiconductors? Direct bandgap semiconductors are having very much. They are also as well conventional. They are used for electronic properties normally, that gives so that advanced electronic properties. Okay, very good. And they are using in case of the optical properties. They give optical properties and they give novel optoelectronic properties. Okay, and they give the novel non-linear optical properties. Okay, these are useful again in case of the photocatalytic properties. They are very much good in case of magnetic properties. Okay, so those are very important like that. Again, yes, in the same all these properties here, so that the direct bandgap semiconductors. Okay, again these direct bandgap semiconductor mostly useful in case of low dimensional physics, so that most of the many applications we get novel applications. So direct bandgap semiconductors give novel properties properties where in low dimensions. Low dimensions means what? It is nano. In case of, so that nano size, when we consider the semiconductors in nano size, direct bandgap semiconductor in nano size, they having very good the novel property. They give novel properties. Okay. So then what are the example for this direct bandgap semiconductor? For 3, 5, it is here what else? Trivalent and pentavalent. Give example. Gallium is trivalent arsenide. Gallium arsenide. Okay. So that and again it is doped with the aluminium. If you dope this aluminium gallium arsenide. Aluminium gallium arsenide. Okay. So that gallium nitrate. Okay. Gallium nitrate. Gallium phosphate. Gallium phosphate. So that these are all the different material. Okay. So that in case of 3, 5 semiconductors, and another one, so 2, 6 semiconductors. These 2, 6 semiconductors, what is cadmium telluride? Okay, cadmium telluride is, so that and then what happens? Another one, cadmium telluride, and zinc oxide. Another one, the 2, 6 semiconductor, and another one, tin oxide, SNO. So that SNO2. This is another one. Okay, so that 3, 6. Another one, titanium oxide. So these are the different examples of 2, 6 the semiconductors. And another one is IV and IV. So this is common with germanium, silicon and germanium are doped with each other. So that at a different concentration, the characteristics of semiconductor is depending upon at what concentration gallium and arsenic are added, gallium and nitrate, gallium phosphate. Okay, so that there are by addition of some transition elements like some metals, all these we doped with a metal. For example, aluminum is doped with a gallium arsenide. Okay, its band gap will change. So and in case of gallium nitrate and gallium phosphate also we add the material. Okay, so that similarly in this case cadmium telluride we add zinc cadmium telluride, like that. And similarly there are number of thousands of semiconductors are there. Cadmium sulfide is there, cadmium selenide is there, lead selenide is there. Okay, so that when such materials are again doped with some inorganic elements like nitrogen, like gases, or some organic semiconductors like that gives the novel properties. Okay, usually this direct bandgap, as I said, used in case of nanomaterials. So that this in case of nanomaterials, in what type of nanomaterials? So that this is used in case of quantum dots. Quantum dots. Okay, quantum dots means what? These are nanoparticles. Nanoparticles. So that how these are useful? So here we know that the quantum dots are the nanoparticles, semiconductors, nanoparticles are the having the lot of applications. So then when these the nanoparticles are so doped in polymers that gives the novel property to the polymer. In case of conducting polymer, all this, so that we use this such the metal or semiconductor nanoparticles. In ceramic also we use these type of the doping of nanoparticles, and the in fluorescent materials we are using the quantum dots. Okay, so collides of semiconductor dots are very much, yeah. So here that is again the light which is emitting from the nanoparticles is depending upon the size of the particles. And another one here, so quantum dots and so quantum wires, so that this is quantum wires, this is also called nano wires. Usually, so that in many semiconductors are grown in the form of the nanowire. What are nanowire? Nanowire having the diameter in nano, and but they are lengthy. So these are also called zero dimension. So zero dimension. We already studied this. So that zero dimensional nanomaterial. This is